0.9982. I guess Peter's for a second.
Did you get the same thing, Ben?
2 seconds. Yes.
I got 0.897. Oh well, either one. So it went from 3.9 meters per second down to a little under 1 meter per second by taking in that. Now, the scenario takes place in the kitchen. I'm not taking temperature into account. I am assuming the temperature is the same in both spots. All right, questions to hear? Last topic. With this idea of Bernoulli, we should be able, as well as barometers, actually everything we've done so far, we should be able to use this to figure out the speed of fluids. So I'll go back to this scenario right here. I have a fluid flowing through the pipe, and I have two little outcroppings which contain fluid. The speed of them, the speed of this relative to that, should be indicated by the relative height here. So this is situation, we'll call those 1 and 2. And I know from Bernoulli that P1 plus 1/2 rho V1 squared plus mg H1 equals the same stuff, but with a 2 there, plus 1/2 rho V2 squared plus mg H2. There is, I drew it awkwardly. That second piece is supposed to be at the same level as the middle of the first piece. This should be up some. I don't want there to be a change in the height, the net height. Okay. All right, so those two terms I wanted to go away. So I know that P1 minus P2 is going to be equal to 1/2 times the density of the fluid that's flowing times V2 squared minus V1 squared. I know that from the continuity equation that area 1, excuse me, area 1 V1 is equal to area 2 V2. So I now have a relationship between V1 and V2, so it's just a matter of which one I want to solve for. And ultimately, I want to get rid of my V1. I think the book gets rid of V2, but so it's A2 V2 over A1. Plug that into here. I get 1/2 times the density of the fluid times V2 squared minus A2 over A1 V2 quantity squared. My V's and R's looking too much alike. I can factor V2 squared out. So I'll get 1/2 rho V2 squared times 1 minus A2 over A1 squared. And that's equal to the difference in the pressure. Let's do some defining here. This is H1. This is H2. So I know that the pressure at this point is P1 all along here. So if I look at the forces, I got its weight pulling down on it. So that's mg, I guess M1g. And pushing up on it is the force from the pressure. So that should be equal to P1 times the area of 1. I need a different notation there. Times area alpha. And down here, similarly, I have M2G is equal to P2 area of alpha. I can make the tubes the same, alpha. So P1 is equal to density 1, volume of 1, G over my A alpha. P2 is equal to density of 2, volume of 2 over A alpha. Oh, G. The volume divided by alpha, or A sub alpha, if my cross-sectional area there is A sub alpha, the volume divided by that is just this height. Once again, there we go. So therefore, we get rho 1 H1G minus rho 2 H2G equals 1/2 rho V2 squared 1 minus A2 over A1, that quantity squared. H1 minus H2. Density is the same fluid, so density cancels out. And we're left with V2, the speed of the fluid in the second half squared over 2G times 1 minus the ratio of the areas squared. So I now have a way of, based on the different heights, the difference in the heights, I have a way of figuring out how fast V2 is flowing relative to V1. Or how fast V2, how fast the second part is flowing. We've already. Yeah. I guess this formula would be for predicting the difference in heights based upon the speed. If we actually solve for the speed. V2 speed at second part is the square root of 2G H1 minus H2 divided by 1 minus A2 over A1 squared. Let's just make sure that this actually will produce a real answer. A2 is smaller than A1, so my denominator is positive. H1 should be bigger than H2 because the pressure is higher where it's moving more slowly. And so H1 minus H2 would also be a positive number. And so we end up with the square root of a positive number, which the math people generally are happy with. Although if you pursue, actually probably engineering too, it's been a long time since I've done engineering. Imaginary numbers are not, just really misnamed. There is a physical meaning to some imaginary numbers. So, but I guess you'll discover that elsewhere. Questions? All right. As said before, the test is primarily engineering momentum, not energy, momentum, rotational motion, and vibrational motion. Anything I ask on thermodynamics or fluids would be at the very basic level. But other than that, that's Wednesday's activity, and then we are done, and I'll potentially see you in January.
I did have a question, not necessarily about.
Oh, okay. So